Okay. Welcome back to our computer development class. So, as we already passed the midterms of the mid of the semester, not the midterm, mid semester, we need to accelerate a little bit the contents. That's why I will push 2 lectures for you to watch by your own. I already pushed one, which includes a presentation about the surf and the integral image, the hard features, and how we can make these calculations. Then I will push another one about the principal component analysis once we finish this transformation stuff. And all of this will be included in the midterm. Okay? When will be the midterm? According to the current time schedule, the midterm will take place. So, yeah, March 31st. Okay? Here in the classroom. Okay?
March 31st.
Yes. It will be a computer-based exam on the lockdown browser. So make sure that you install it and make sure that it's running on your computer. Okay?
Same time in the class, please.
I'm sorry?
Same time.
Yes. The time simulation. Okay. Now let's go to today's lecture. So far, we learned about features. We learned how we can identify the points of interest. We learned how we find the descriptor. We covered 2 types of descriptor last time. And the lecture I posted, including also one more descriptor, the surf descriptor. And we learned how we can do the matching and judge the quality of the matching process using the ROC curve and the ratio distance between the first and second option, minimum distance. Now the question is, how can we use this? Assume that I captured 2 images for some place like this. So those are 2 pictures captured for the same location, okay? And I want to align them together to get an extended view or extended scene for the place. Now, what I'm doing right now is just copy and paste. So try to copy the missing part from the first view and paste it to the second one. Now, if this is a correct matching, now that the 2 pictures match, are they homogeneous?
Looks like it.
Okay. Let's assume this is
Oh, I don't see it.
like
Yeah.
stair or some support like this. This part should be aligned, right? Is it aligned?
No.
So are they matching? No, they are not matching. And based on that, many other features that you think they are matched, they are not matched. Okay? Then how I can do this matching, how I can adjust the first one or the second one or both to make this matching process. So I want to achieve this view at the end. To make this one line, this one is the continuous of the second one, and this filling the gap between the second one. That's what I want to achieve. How can I do it? Okay. Based on that, as you can see, this is the first image. This is image number 1. And this is image number 2. What did I do in the first one and the second one to achieve this view? If you take a smaller look with the details, you will see that I adjusted the location of the pixels from its original location to a newer location. What does this mean? You see this line? It's tilted this way, right? I make it straight to can match it with the other one. Same here. What does this mean mathematically? If I want to describe this with math, how I can describe it? They said I will do something called warping. What is the warping? If it's similar to image filtering, they said no. In the image filtering, I'm having input image of size X and Y. The output of the filter will be image with similar size if I'm using the correct stride and padding. Again, I will receive image with the same size. So I input, this one is 100 by 100. I'm receiving here 100 by 100. In the filtering, what exactly will happen? The pixel value will change. So this will be different from this. So if this is light, this will be maybe darker, maybe sharper, maybe more fuzzier. Okay? So the pixel value in the filtration process is changing, but the pixel location is same. So this is 1 and 1, same here, 1 and 1. Pixel location didn't change. What changed what? The value of this location. Okay? That's what we call filtering. That's, if we are talking mathematically, the value of the pixel is the range of the function. So if you have function, f of x equal x squared as an example, where is the domain and where is the range? Where is the domain and where is the range?
The domain is infinity, like the x axis, the range is like 0 to infinity.
So the domain definition is the possible value of x that we can apply as an input to the function, right? So here, x can be any value from here. That's what we call domain. Range is the output value, the value of the y, the value of f, corresponding to this input. So here, the range is from 0 to infinity. The domain from minus infinity to infinity, range from 0 to infinity. Now, here, the filtering is changing the range, change the value of the pixel itself, but it doesn't change the domain, it doesn't change 1, 1. So the location is the same, but the pixel value change. On the other hand, the warping, it changed the domain itself. What does this mean? It means that if this is my original image, and this is the pixel at 1 and 1, I will move the pixel from 1 and 1 to another location. Now, I didn't change the value of the pixel. No, I changed the location of the pixel. So if this is the original function, I'm shifting it or moving it from the position here to another position. So I'm changing the domain. Here, the location is fixed. By I'm changing the function itself. Here, I'm changing the domain itself, moving it from the certain location to another location. Okay, that's what we call image warping. Why is it important? What is the relation between this and what I'm describing? Actually, that's exactly what we did here. So this pixel was here in location, let's say 101. I moved it to be in location 85. The same exact pixel. I change its location to match the other one. So what we are doing here to make this match between the two images is a warping process, or we are calling it transformation. Okay, so the warping process is the process of changing the domain of the image for any purpose. So for example, assuming that I have this input image, if I'm doing regular filtering, I will receive something like this. Sharpening, edges, whatever what you are doing, but the same exact size with changing the pixel value. On the other hand, if we are doing warping, I can change the entire shape. So this image can be stretched, can be sheared. Sheared means it will look like this. Apply shearing force. So, okay, I can convert it into ball. I can do anything. Okay, that's what we call the warping or transformation. What are the common type of transformation I can apply to the image? The three most common transformations are translation, rotation, and changing the aspect ratio. Those are examples. There are so many others, like scaling, like shearing. All of those considered to be transformation. So here, I'm translating the location of the pixel to another location. Here, I'm rotating it. Here, I change the aspect ratio. Okay? Now, how I can describe this mathematically? This said, simply, I have to define transformation process function that I can apply it to the original pixel value to generate a newer location for the same pixel value based on this transformation. So the input here, not the value of the pixel, no, it's the location of the pixel. The input B, location of the pixel. And the output is the new location. Okay? So if this pixel, for example, at location, let's say 5 and 10, the value of the pixel itself is 100. Then I will apply the transformation. It will generate a new location. I will move this 100 from here, put it here. That's it. So my goal now is to calculate the new location where I will move this pixel value to it. How? By finding this translation or transformation matrix. Okay? We will assume that this transformation is linear. What does this mean? Means I can apply it as a matrix multiplication to the original image. So all the transformation that I will apply right now considered to be a linear transformation. What is the definition of linearity? If you recall from the beginning of the semester, when I said some process is linear, means what? I said the function is linear.
So two-dimensional. Okay.
This is the definition of linearity. If you have f of x plus y, this will equal f of x plus f of y. If you have f of ax, this will equal af of x. If the function satisfies those two conditions, it's a linear function. Okay? So here, we will assume that the transformation here, or the transformation is a linear transformation, and we will represent it by a matrix. So this will be a matrix. This B will be a vector. The result from that will be another vector. So this is the input location. And this is the output location. Okay? Now, what are the possible values of this T that can achieve the transformation that we described? Let's take them one by one. I will start by the scaling. So assume that I have an image like this, and I want to stretch it. Scale it. In this case, this you can define the matrix T to equal S, where S has the scale factor on the two main diagonal elements and 0 elsewhere. So any value was here, it will be scaled. So it's like shifting. Okay? Can I shrink? Now I'm scaling up. Can I shrink? How?
Decrease the scaling factor.
Actually, let me here. So assume that okay. Assume this version is a stretched version from the scaled version. Okay. Now I want to return from this. I have this. I want to return from this. Can I do that? What would be the value? Okay, think about it. How about the rotation? Can I rotate it? Yes, I can. In this case, I will use something called rotation matrix. It will take function of the rotation angle. So I will rotate this picture or this image with an angle theta. In this case, I have to multiply each pixel location times this okay. Can I return back? Like if I have this, can I return to this? The answer is yes. In this case, and here should be the inverse of this. Luckily that this one, this matrix inverse equal the transpose of it. If you just take the transpose, it equals the inverse. So this will equal cosine theta, sine theta, sine theta, minus sine theta. So you can go back and forth from here to here or from here to here. Okay? Is this clear? Can I mirror? Meaning, I'm having this image right now. I want to mirror it this way. Make this wheel to the right rather than to the left. Can I do that? Yes. In this case, I will assign x dash equal minus x, y dash equal y, because I'm not changing the y value, I'm just flipping the x. Okay? Can we write it in a matrix? Those are the two matrices for mirroring. Okay? If you want to make mirror across y equal x, means what is the meaning of making mirror across y equal x? How it will look like?
So like a horizontal mirror? Horizontally?
But what is the shape of y equal x?
A straight line? Yeah.
So imagine that you are mirroring around this. How it will look like? This wheel will be here. And those building will be flipping down. Isn't it? Can you imagine it? So this will be here. Put your hand like this and flip everything. So this wheel will be here. All those building will be, this one will be here, this one will be here, and everything flipped down. That's how mirroring around y equal x. But it has the same shape, it's not changing. Okay? Okay. How about translation? If I have an image like this, and where this is 0 and 0, and I moved it from this location, so it become like this. This is what we call translation. Okay? This is considered to be a transformation that we can apply the matrix for it. The answer is no. Because here, I'm adding to the x value and I'm adding to the y value. In this case, it's not linear. There is no linear transformation can be achieved from that. If you are adding to the variable, this is not linear. The linear is the multiplication only, not the addition. If you add, it's not linear anymore. Okay? So this is not a linear operation. So I can't use or consider the rotation, the translation as a linear transformation. So can we conclude the linear transformation? We said yes. The linear transformation is any transformation that can fit within the 2 by 2 matrix multiplied to the original coordination to produce a newer coordination that do some process or modification in the original image. Example like this, the scaling, the rotation, the shearing, or the mirror. What are the properties of the linear transformation? First, the origin is not changing. So in all these examples, origin here, the origin is here, is not changing. Origin here, origin is here, is not changing. Even if you are doing the mirroring, the origin is not changing. Origin still the same, not changing. So this is one of the properties of the linear transformation. Origin never change. Lines stay lines. If you have any straight line in the image, it will stay straight line, will not change any lines. Okay, so if you have a line, it will never convert to curve, or if you have a curve, it will not convert to line. No, lines are lines. Parallel lines, still parallel. No change in this as well. If I have any parallel lines, stay in parallel, no matter what type of transformation, linear transformation you are applying, it will stay parallel. Ratios are preserved. If something bigger than another, after rotation, this thing is still bigger than the other. So ratios preserved, no change. It's a closed under composition. What does this mean? It means that I can apply one, a second, a third, a fourth, a tenth, one after the other, and the combination of all of them still linear. So I can apply scale, then rotate, then mirror, or vice versa. Doesn't matter which I apply first. And the combination of all of them will be linear. How this is possible? Simply apply the math. One of them is for the scale, another for rotation, another for sheen. If you multiply 2 by 2 times 2 by 2 times 2 by 2, the result will be what? If you multiply 2 by 2 matrix times 2 by 2 matrix times 2 by 2 matrix, the result will be what? Still 2 by 2. So it will be also one of the linear operation. So it doesn't matter what type of operation you are doing, you will end up by having a linear operation. Okay. Now, and try now to find a way to change the translation to be included with this matrix. How can I do that? They said, simply don't work with the 2 by 2. Shift up a little bit. Go to the 3 by 3. So work on the 3 dimension. So we'll assume now that our image is just a plane in the 3D view. So this is the 3D view. The image is like this, in this plane. Shift will happen, will be considered as a changing in the plane. In this case, if I make it fixed plane, I can represent any position in the image with X, Y, and fixed plane 1 or W. Call it however you want. If you want to make it fixed at 1, at level 1, that's okay. Or if you want to make it generic, then you can make it W. Then the 2D coordination will be a normalized version. Doesn't matter. This is okay, this is okay. In this case, I can add the translation to be part of the third column. So if I didn't do any change here, and this will be the translation, then multiply this times X, Y, and 1, and add. The result will be what? So now, this multiplication will result in a translation, and this matrix will be linear matrix. But it's not 100% linear, because now I'm adding one extra row that I didn't want. That's why we will change the name of this technique, and we will call it affine transformation. So now we have two types of transformation. First one, is the linear transformation, which can be described by 2 by 2 matrix. The other one is the affine transformation, which upgraded the matrix a little bit to be 3 by 3. But for the affine transformation, this third row is fixed. I'm not changing it. It's included, yes, but it stay here like this forever, 0, 0, and 1. Why do we need it? Because it add the translation. So the definition of the affine transformation is linear transformation plus translation. Okay? So linear transformation plus translation equal affine transformation. Listen, this and this will give you that. If those will be representing linear transformation and those will be the translation, I can write this affine transformation matrix to look like this. So it has A, B, C, D, E, F. Those are the linear process and those are the translation. But this one must be fixed. Okay? 0, 0, and 1 forever. So if I'm using translation only, then it will look like this. If I'm using scaling only, it will look like this. If I'm using shearing only, it will look like this. Rotation only, it will look like this. Can I combine them? Yes, I can combine. So this is originally linear. Sorry, this is originally linear. This is originally linear. This is originally linear. This is the new one that has been added for the affine. So I can say that the linear transformation is a subset of the affine transformation. So this is the affine. Okay. Is this clear? Based on that, we can study the properties of the affine. The origin in this case does not have to be in the same place because we included translation, and translation will not keep the origin. It will change the origin to a different place. So origin does not necessarily map to the origin. But lines will still map to lines. No change in that. Parallel lines still map to parallel lines or remain parallel. Ratios preserved. Something bigger and smaller, the ratio will have no problem. Closed under composition. So if I apply any one of them, then another one still will be considered affine. Any problems so far? Okay. Is this affine? This is the image that we showed at the beginning, right? Is this an affine transformation? Again, for simplicity, look to one of them and this new one and tell me, is it affine or not?
Is the origin the same?
You tell me. The origin is not the same because it was here, it shifted down. So it's not the same. Let's check the properties. This line is parallel to what? Let's say to this one. This was parallel to this. This was parallel to this. Now move here. This line still parallel to this. Okay. If this still parallel to this, not really. If you look up there to those two lines, are they parallel? They look parallel to you? Come on, none of you studied geometry before? You don't know the parallel lines?
Yeah, well, it looks like
They look
changed.
So they are not parallel. So this is not an affine transformation. No. Then how I can, or what type of transformation happen here that convert those into these? Actually, they said, I still need one more transformation where I can play with the third one. Why I'm keeping it fixed? Keeping it fixed means what? Meaning I'm working on a plan, right? But I don't want to work in a plan. I want to get the flexibility to move in the 3D. Stretch this up, pull it down, do whatever I want. Meaning, change this third row. Okay? They said, okay, change it. What will happen if you change it? They said, if we add any two values to those one, I can add a 3D view for the image. So exactly like making this side and pull it to the back. So now what I did so far, we change it to be surface, not in one fixed plan. It become like a surface right now. Okay? Only by changing those two values from 0 and 0 to another value. They call this one a homography or homographic transformation. In some books, you will call it planar perspective mapping. What are the properties of this transformation? They said it's exactly similar to the affine, but the third row is not 0, 0, and 1. It has other values, which mean that I will generate W. In the other one, the W was 1, fixed forever. Here, no, I'm generating W. So from the 2D, I'm generating 3D. If you try to do the math for that, apply matrix multiplication, you will receive this vector. In this case, the W will equal this value. Okay, but do I have in my hand the image as a plan, or I'm having a 3D image? What do I have in my hand on a paper? Plan or a 3D image? Plan, right? Means I need to project this W to this plan. How I can get the projection? Simply divide this over this and this over this. So if I do this division, that's what I will receive. So the coordination after this adjustment will end up to be like this. Now, if this value equal to 0, can it be 0? So Gx plus hy plus 1 equals 0. Now this can be 0. If g equals 0 and h equal minus 1 and y equal 1, or you can play with that. So this has several values. It's a linear equation actually. Okay? If for any reason this will equal 0, this denominator will equal what? 0. So this ratio will equal what? Will equal what?
Zero.
What? Someone said something. Infinity. Because this is non-zero. Divide non-zero over 0 will end up by having infinity. What does it mean to have infinity? Mean that you will have something called vanishing points. So you can have points in your image go to infinity, vanish. Okay? So, as I said, this view or this type of transformation can project you to the infinity. It generates a 3D, third dimension for your image. Even if you can't see it in the 3D, because we are reprojecting it back to the 2D, but it changed the view of your image. Okay? Which is exactly similar to what we have here. Right? So we push it this way and be like this. We pushed it this way and be like this. Then match them together. That's why it's a homography transformation. So using this transformation, I can project a view to a completely different view. If it was a 3D, I can project it to 2D, like this one, as an example. Those area was like this. I can find transformation, homographic transformation, that transform it to this view, to become parallel. These doors, I can find transformation to project them to this view, to become parallel lines, and all of them perpendicular. Okay? So those type of transformation can be used to convert the third dimension or the third part in the image and put it back to a 2D view, and vice versa. Okay? So that's exactly what we did here in this one. We found the homographic transformation from those two to produce this one. Based on that, what will be the properties of the homographic transformation? First, homographic transformation can be considered as the superset of all transformations, meaning the general transformation is the homographies. Subset of it, the affine. Subset of it, the linear. So this is the more general transformation. Okay? The view of the homographic transformation is 3x3 matrix, not 2x2, and this one is not fixed. No, it can be variable. In this case, of course, origins may not stay in the same place. It can change. Lines will stay lines. But if they were parallel, they don't have to be parallel after transformation, as I show you in the example here. those were parallel, here, not parallel anymore. Okay? So parallel does not remain parallel or doesn't have to be parallel. Ratios are not preserved because now we have a 3D view. Something may be far and big, but for me to look small. Something that can be closer and small, it will look big. So the ratios will be destroyed. I'm not working with the same plane right now. I'm working on the 3D. Okay? So ratios destroyed. It's closed under the composition, meaning apply multiple transformation one after the other and still close under the homographism. Okay. Now, in the example or the matrix that we apply here, we put the value of this element is 1 because we are mapping from 2D to 3D. So that's why here was 1. So this have nothing to do with never be 1. Can we change it to another value? They said, yes, we can. So we can put it a general value like the others. But in this case, the value of the vector or the length of the vector that include all those items must equal 1, which means those values must be normalized. Must. If this value is not 1, this means this has to be normalized. Okay? And this can be considered the shape of the general shape of the homographic transformation. So as we stated, linear is a homography. Affine is a homography. But homography is not linear. Homography is not affine. So if I would give you now 2 images, it's better to start to find the linear transformation between them or go directly to the homography. According to what we have so far. And you got 2 images. Image 1 and image 2. And I asked you to find the transformation between the 2 images. What exactly will start to do? Find the linear first, didn't work, I go for affine, didn't work, go for homography, or we'll go directly to the homography. What do you think?
Like we go from linear because we gotta see if the properties are changing.
Okay. In linear, you have how many parameters to work with?
2.
Actually 4,
Oh, my bad.
because we are working with 2 by 2 matrix, right? In affine, you have how many parameters?
That was W. By 3.
6. Only 6, because those are fixed. So here, 6 parameters. Here you have how many parameters to work with? So some people think that it's better to go with a small number of parameters, which is the linear. If it will work well, I save time. If it didn't work well, I will go with the more number of parameters, which is the affine. If it worked well, I'm fine. If it didn't work well, then I will go with the homography, which is the highest number of parameters, and it's more generalized. Okay? Unfortunately, this technique is not logical, because in most cases, you will find yourself going up to find better results. That's why mostly we start automatically with the homography. Okay? Because homography implicitly has the affine and the linear inside. So if I found those 9 parameters, it can be 6 of them in the affine or the linear part. So I don't need to make or repeat the same process again. Okay? So always go with the homography unless you are certain 100% that the transformation is linear or affine from the beginning. If you are certain that the transformation is linear or affine, then go with that first. If you don't know, automatically go to the homography because it's the safest option. Okay? Any questions? So, we learned now how can we do the transformation from one view to another, and we learned the names of those transformations. There are some other names for the use transformation. One of them is called the rigid transformation or the Euclidean. The rigid transformation or the Euclidean is a similar one to the affine, where it has rotation followed by translation. The only difference is the original affine, including a fixed third row. Here, we are having 2 by 2 and 1 column separated by itself. Here, I have a total number of parameters of 6. Here, I'm searching only for the translation part. The more generic one is the projective or the homography, which is the one that can do all the, or find the 9 parameters for you. Okay? Now the question is, assume that you're already working to map or translate image like this, which is of size 10 by 10, to another image that will look like this, of size 10 by 20. Okay? The question is, how many pixels here? 100 pixels, right? How many pixels here? 200 pixels. If I understand correctly, what we are doing is we just move the pixel value from some location to the corresponding location here, or the new location here, right? But the number of pixels is not 7. What could I do? Bring pixels from my pocket? Invent pixels? What should I do? Here, I'm having 100 pixels. Here, I want to fill 200. From where I will get those extra pixels? How can I get it? Any idea? Something that you did similar assignment to? Does it?
Or the
You will do super resolution here? Is this a super resolution part? You are close.
Is it the window size? Anything to do with that?
Window size? What do you mean by window size?
Like increase the window size by like padding?
interpolation. Always, always, always do interpolation. Interpolation is your friend. Okay? So I can move those here as an example. So this one will be here. Then I will shift one, next, shift one, next, shift one, next, shift one, and so on. Then apply interpolation filter. Whatever the type of filter you want. Linear, cubic, bicubic, Gaussian, whatever the type of filter you will use. So you will always need to use interpolation if you are doing a transformation or wrapping. Always. They are come next to each other. Okay? Because you will never be able to fill the same number of pixels from here to here. Never. Okay? Like for example, if you are doing this, you see how this stretched from here? How the shrink from here? From where I got this extra pixel? Interpolate. Okay? So we always require interpolation if we want to have or use homography or transformation in general. Okay? So the problem that we always face is if we are moving from one given image to a translated or transformed version. Theoretically, we will find the location, the new location of this location, then move the pixel value from here to here. That's how originally it should be. Okay? But unfortunately, it's not that easy. There's some cases where when you are moving forward, you will find that you are go to pixel or value in between. That include fractions, as an example. Or something that's not suitable with this location. Maybe negative value. Anything that you may think unlogical, okay? In this case, you need to normalize and adjust the location to the new location. If for any reason you are fitting a place that doesn't exist, always try to interpolate. And watch out, interpolation always happen with pre-filtering, exactly like we are building the Gaussian pyramid. When we are building the Gaussian pyramid, always we do what? What are the steps of the Gaussian pyramid? Seriously?
Convolution.
Okay. Before convolution, you are doing something. Or sorry, convolution for with what first? I have image. And I want to build a filter, sorry, a Gaussian pyramid for that. What exactly I'm doing?
You applying the kernel. Well,
Which is
the Gaussian kernel.
then?
Then you shift it.
Okay, I'm applying the kernel to the image. So this is my input image. I applied the kernel. Then what?
You sample it.
Exactly, sample down. Then apply Gaussian kernel again. Then sample again. Kernel, apply the kernel again. Then sample again. That's how the Gaussian kernel, the Gaussian pyramid is working. Plur, sample, plur, sample, plur, sample, and so on. Okay? So always, if you will do any interpolation, sampling up or sampling down, you have to pre-filter. Okay? Also, I can use it to return to the original image. So assume this is the new transformed image, and I want to return to the original image. In this case, I can also interpolate the position of the image and find the value of the pixel. Okay, so the process of interpolation for the pixel value or the location value, both of them can be applied in this case. So I can interpolate the pixel value and I can interpolate the location value itself. Okay? Is this clear? Any problems so far? Okay. So now we learned about the transformation and the types of those transformation. And we understand that something like this is a homography. But the question is, how can I find the transformation that convert image from some specific view to another? So I have this right now, and I have this, and I have matches in the points. How I can find the transformation between them that convert one to another? We'll start first by the simplest case. What is the simplest case? Translation. Assume that you have image and another one. And we found features here that match the feature here. So we know the points of interest here that match with the other one here. This is done. And I want to find the translational transformation that move this to this. So I know from the beginning that this will be moved to this just by translation. That's it. How can I do that? We said simply, this is called x1, y1, and this is called x1 dash, y1 dash. Simply subtract them from each other. This is a translation, right? So x1 dash minus x1 should give you the translation. Right? y1 dash. Very simple. Let's go home. Finish the problem. Right? Unfortunately, no. Because if you use the first one, you will get xtyt. If you use the second one, you may get different xtyt. If you use the third one, you will get a different one. So which one of them is the correct one? Okay. So in this case, we're having two values I'm looking for, but I have many number of points that can satisfy or can be used to solve the problem. So in that case, I will try to take the difference between each one of them. Then I will take the average. So the translation for the first one, the translation from the second one, translation for the third one, then I will average them. Okay? Now, is this a good strategy? The answer is not that much. Or we can look to the problem from another point of view for it. What is it? I can look to it from the more mathematical perspective. What is this mathematical perspective? I will assume that the new one point has been generated from the original one plus the translation. How many parameters here I want to solve? This is unknown number 1. This is unknown number 2. How many unknowns in this equation? 2, right? 2 simultaneous equations in 2 variables. Can I solve them? Yes, but in 1 point. If I have only 1 point. But here I have multiple points. So that will make us in something called overdetermined system. Because we have number of points more than or larger than the number of variables. 1 point only can solve the problem. But I have here about 6 or 7 or 10. So I'm adding extra information for nothing. Okay? In this case, how can I solve it? They said, very simple. I will use some concept called least square concept, which use the residue point. Meaning, for some specific point, or for each point I have in the transformation, I calculate the newer version or find the newer version. Then I will subtract this minus this. So xt will equal xi dash minus xi. Then I will solve or convert the problem into a matrix problem. So I will have residue for x and another residue for y. This is the unknown that I'm searching for, and this is the unknown I'm searching for. Now, this one will be repeated for all the residue of all the points. Okay? Now, can I write those or rewrite them or formulate them in a matrix form? Answer is yes. I will try to. The value of the transformation will equal x1 dash minus x1. At the same time, xt equal x2 dash minus x2. At the same time, xt equal x3 dash minus x3, and so on. Then I will do the same thing for the y. So the y will look also the same. Yt equal y1 dash minus y1 equal y2 dash minus y2, y3 dash minus y3, until I arrive to yn dash minus yn. Then try to minimize a cost function, which is the sum of the square of those two residues over x and for y. That's why we are calling it least square, because we are trying to minimize the square of the error. Okay? Now, the solution for that is exactly the build of this matrix. So the difference, or this translation, is just the difference between each one of them. Can I solve this matrix? They said let's put it in a matrix form. So this matrix has a dimension of 2n by 2. 2n row and 2 columns. Why 2n? Because I'm separating now the first one for x, the second one for y. And I have n sample, so I have 2n. By 2, because I have x and y. This one are the two variables I'm looking for, which are the two translations. This one also will have the dimension of 2n by 1, because those are the errors, the difference. My goal is to find this unknown. Can I solve this matrix? I give you a system. AX equal B, and they ask you to find the X, what should you do?
A inverse.
What? One at a time. Won't start. What?
A inverse.
A.
Inverse.
So, right? Can I apply this here? No. What is the condition for the inverse? What is the condition for the matrix to calculate the inverse? When I can say that this matrix is invertible. It has to satisfy two conditions. Condition number one has to be square. If this is square matrix, condition number one disappears. Condition number two is the determinant of the matrix must not equal 0. If those two conditions satisfy for A, I can invert it. Does those two conditions apply to A? No. Then what should I do? Can I apply this? No. Then how can I solve it? Any suggestion? They found some mathematical trick. What is this mathematical trick? They said, simply, I will apply or multiply A transpose on both sides from the left. So I will multiply A transpose here and A transpose here. What is the dimension of A transpose?
2 by 2n.
2 by 2n. So can I multiply it or no? Yes. Now, A transpose times A will equal what? System converted to this equation. Something 2 by 2 times 2 by 1 equal 2 by 1. Can I apply this rule now or no? Yes, because the condition now satisfied. It's a square matrix. So I will check for the determinant and convert it to calculate the inverse and send it to the other side. So I can say that T will equal A transpose A inverse times A transpose B. Okay, so this is a trick we always use if we want to solve for variable, but the equations are not square. Okay, that's how it will end up. Okay, does this mean that it has one solution or have multiple solutions? This equation will have one solution or multiple? One optimum. Because remember, what we want to do is find the minimum of that. So the optimum. So we have one optimum solution, which is this one. Okay? Does it have other solutions? Yes, it has other solutions, but not optimum. This is the optimum one. Okay? Now, if you want to interpret the meaning of this equation, it's exactly as if I'm having several points like that in the space, and I'm trying to fit a line between them. This is exactly the same problem. So I'm having a line, and I will calculate the error between each point and that line. This error is the residue. So this is the residue for this, residue for this, residue for this, residue for this, and I'm trying to minimize the summation of all those residues over both x and y direction. Okay, so it's a minimization of the same exact thing. So why this problem considered to be a linear regression problem. Okay, so I can convert this linear regression problem into similar thing. Again, I have two parameters here, which are the parameter of the line. I'm trying to find the equation of that line. What are the parameters of that line? M and B. So those are the parameters I'm looking for. I'll calculate the residue for that and try to minimize them, which will end up by having equation like this. So I can apply the same exact trick to find the value of M and B. Okay? Again, remind me, I'm doing all of this to work on which transformation? It's only what? Which include only two parameters. Is this a linear? What if I have a linear one? How many parameters I will have? Four parameters. If I have a fine, can I use the same technique with those 6 parameters of affine? So in the affine, I know that this is 1 fixed, this is 0, 0, 1 fixed, and this is 1 fixed. I know. So the only 6 parameters I'm looking for are those. Can I use the same trick? Yes, I can use the same trick. So in this case, I'll calculate also the residue over the x values and the residue over the y values. Again, those are the x, those are the y. So in this case, I will have axi plus byi plus c minus xi dash. Same for that one, for the y. And I will try to build the same exact matrix that can work for all of them. Okay? The only difference is here I have how many parameters? 6. This will be 2n by 6. This will be 2n by 1. Again, I can apply the same exact trick and I can find the value of A, B, C, D, E, F. Model. It's very straightforward. Okay? How about the homography? How many parameters am I having here?
8, 9.
9, actually. We said we will generalize it. So we are working on 3 by 3 matrix right now. So we have 9 parameters. And the same concept apply to it. Let's see. So I'm having those xi and those are the yi. Those are the original and those are the transformer. Those are the dash. Now, what is the relation between xi dash and xi? Here is it. What is the relation between yi dash and yi? Here is it. Is it linear? Does it look linear for you? If we have the numerator only, like the affine, then it looks linear. But it has what? Denominator. And the denominator is the combination of xi, yi also. So the equations that produce here, unfortunately, non-linear equations between xi and xi dash. Can we solve it in the same concept? The answer is no. Then how I will solve it? They said I will try to twist this a little bit. So I will multiply this to this side. So it will be xi dash times all of this equal this numerator. Same here. Then what? Then I will rearrange it to look like this. I will have each one of those in a vector, put them all on one side, and try to separate the coefficient to be multiplied times them. But the drawback that I'm moving this from here to this side, because I'm having here also H00, H01, H02. So some here and some there. It will end up that I'm having this equation. Is this a linear equation? This down is a matrix of the size 2 by 8. Oh, 2 by 9. And this is 9 by 1. And the result here is 2 by 1. And this is for only one point. What if I apply it to the multiple points? That's how I will end up. One matrix, which is 2n by 9. This is 9 by 1. And this is 2n by 1. Can I solve it the same way? Answer is no. Because here, I'm having what? A zero equation. Here I don't have b on the other side. So I can apply the inverse and multiply. No, I can't. Then how I will solve it? I'm trying now to find the value of h, non-zero value of h, that produce the zero value for this. Which means what? Which meaning that I'm trying to find the eigenvector of A transpose A. So this technique is similar to the one that we had, or the problem that we faced when we discussed the corner detection, if you recall. So we'll try now to find the eigenvector of this matrix times its transpose. The value of the vector with the smallest eigenvector will be the solution for my equation. So I'll calculate A transpose A and find the eigenvalue. For that, choose the eigenvalue with the smallest value. The corresponding eigenvector for it will be the one that achieves the best solution. Okay? So now, to find the transformation, I have two problems or two techniques. If my transformation is linear or affine, I can easily convert the problem into a least square problem. And I can solve it using the technique of the residue by having A transpose A inverse times A transpose B. Very straightforward. Where B is the difference between xi dash minus x minus xi for all the value. You are working with homographic transformation. In this case, I calculate the A transpose A, and for that, I calculate the eigenvalue, the minimum value of the eigenvalue, I'll get the corresponding eigenvector for it, and this will be my solution. Either way, this or this can be used to solve our problem. That's why I told you, some people use the concept of the linearity and affine first, because this technique is easier, rather than going to the calculation of the eigen. Calculation of the eigen takes some time. This one is straightforward. But don't use this technique if you don't know what type of transformation you have in the image. If the image is not clear, it's affine or linear or what, then based on what you will do your job, no one knows. Okay? So selecting the transformation should be a tricky step that you should take care of if you decide to work with the linear or the affine. They are easy to calculate, yes, but it may not satisfy your problem. On the other hand, if you decided to go with the homography from the beginning, the calculations will be a little more tough, but it will be more general. Okay? Okay. So, based on what we have right now, what will be the steps to find the alignment or the transformation between the two images? First, I will find the points of interest. Based on those points of interest, I calculate the features. For those features, I will do the matching process as we discussed last time. After I found the match, I will decide if I will use homography or affine. If I decided to work with homography, in this case, I will use either the least square method or the eigenvalue method, depend on the problem I'm trying to solve. Okay? Is it always will go that straightforward? The answer is no. Always there is a trick. What could be the trick here? Outliers. The outliers can destroy the transformation because they are not matching. Like this is not this. Then how you will convert this to this? It's impossible. Same here. This is not this. Then how you will make this conversion? And we discussed before how we can work with the outliers. How?
Thresholding somewhere.
No, we said there is some algorithm. Exactly, the RANSAC, the random sampling. So always, when we are working with the transformation, we don't work with the whole entire sample. No. We sample them. We choose sample from here and the corresponding sample from here and find the transformation. Then repeat it again with a different number of samples. Repeat it again with different sample until we find the best one that satisfies everything. And we are doing this to skip those outliers. Okay? So always use the Randstad with the transformation matching or transformation find. Don't work with the transformation directly on all the images. No. Always try to skip or sample to avoid those outliers. Okay? Any questions? Okay. Do you have a paper? Or you stop using it? Paper.
I watched a lecture.
Well,
I watched it on Zoom.
yeah, I understand. But this is not what I'm saying. The OpenCV can provide an easy way to find the points of interest, calculate the feature vector, then make matching, and based on that, calculate the homography. So you don't have to work over all of this yourself. But again, the calculations for that is not that complicated. The most complicated part or the most time-consuming part is calculating the features, even by SEFT, SURF, ORP, or any other type of features. This is the most time-consuming part. All the other part, as we saw in the presentation, is trivial and straightforward. Just waiting the code to open. So, as we saw last time, the technique we can use to install the OpenCV and the OpenCV contribute library to the virtual environment that we created at the beginning of the semester. So who installed it to his computer? So based on that, we started last time to learn how can we extract the features and calculate the points of interest, and build on that, we said we can calculate the required feature using any technique of ORP or the SEFT or SURF, or any, if you want, ORP or any other. Now we want to add one extra step. So that's exactly what we did last time. We start by creating the detector. And for this detector, we said that there are two methods. First one called detect, which can be used to find. Thank you. Detect can be used to find the points of interest or the key points for this specific technique. Here it's SEFT. If we are using the SURF, it will detect the technique for the SURF. For the SEFT, we can specify the initial sigma value to start with. Remember, we said that we create multi-scale with multiple sigma and find the difference of Gaussian based on the technique we started with the SEFT. With the SURF, if you watch the video that I posted on Canvas, which describe or have a more description about the SURF, it worked with the Hessian matrix rather than the Laplacian. So it add two extra components and make the problem more numerical. So for the SURF, we add here the threshold for the SURF. for the Hessian or the minimum Hessian value, we will accept. The detect method will return the key points or the points of interest I want to work on in the, or I want to find, or I can find in my given image. Okay, so this is the example for the surf. Yeah, this is for the surf part. I'm using detect, so it could return the key points, and based on that, I can use the drawing operation to draw them. Assume that I found the key points and I want to calculate the feature. So in this case, I will use detect and compute. So after creating the surf detector, again, I will specify the minimum Hessian value. I will stop or clip the features at it. Then I'll calculate, detect, and compute, which will return the key point and the vector description, both of them. So this is the points of interest, and this is the description for image 1 and image 2, the two images that I want to match together. Next step, there is something in OpenCV also called descriptor match. So this one has been designed to do matching between all descriptors found here and all other descriptors found here. Remember the matrix that I told you that will find the distance between each vector here and the other vector here. Last time, this one built this matrix. Then it find the minimum matrix or the minimum distance between them using brute force technique. Meaning, I will keep try and error, find the minimum until I find the minimum between all of them. If I found matches, in this case, I can draw them or I can go and find or plot and see exactly what match with what. So for example, in this example, I'm having this is image number 1 and this is image number 2. Image number 1 is only for this box. Image number 2 has many boxes. Here, I'm detecting the features for the box, and here I'm detecting the feature for everything. And I'm trying to make match. As you can see, some of the matches are correct, like those. See those? All of those are matched here correctly. And some of them are outliers. This is outlier. All of these are outliers. They are matching with something from here, but it's not correct. Okay? That's why I should not work with the whole entire match. Here, I'm using the whole entire match, which is not correct. If I want to find matching between all of them, I have to choose the top match. That's exactly what we are doing. Give me 1 second. Yes. So here, I'm thresholding the match. Try to ignore part of the wrong or bad matches. Based on that, I will use the one or the matches that best satisfy my requirement. And based on that, I can choose or find which one worked for better for me. So if I'm trying to find or plot that, see the difference between this and the other? The other one, the match here was what? Everywhere. Here, almost all of this here match here, except what? How many outliers here I have? Maybe I need magnifier. How many outliers? To zoom out a little bit. How many outliers? Only one outlier. Why? Because I threshold the matching distance and choose the top of them. So if you didn't do the thresholding and choose the top, you will end up by having lots of outliers. Here, you have only one. And this I can ignore in the ransack. Okay? Is this clear? So assume I did this, and I'm working correctly now. I need now to move to the homography. I want to find the transformation that moved me from this location to this location, or vice versa. How can I do that? In this case, one second. Yes. Okay. After I find a good match and draw them, I will start to create a matching point by creating or trying to find the homography between those object seen and the other scene. And I will add the ransack, which means sample. Don't work on everything, just sample part of it. The outcome of this thing should be the transformation matrix. The transformation matrix H. Based on that, I can transform either the box to the scene or the scene to the box. Either way, this or this or this or this. And based on that, I can even highlight the object. Because I know now, those corners I already know. This here, this here, this here, this here. I know those coordinations. And I know that it matches with those. So I'm trying to find the coordination from this to this. If I found for the features, I will apply them to the corners and I will highlight the objects. Is this clear? So I'm using now the good match to find the homography between here and here, and I'm using ransack to ignore the outliers. There is always some outliers, one or two. This is something that we can't control. Then, based on this homography that I found, I will convert the coordination of the original box using this to the new coordination of the object. Then I will draw them on the object to highlight it. Is it clear? So it's straightforward. Start by creating the surf feature or SERF, it doesn't matter, whatever the feature technique you will using. Then detect and compute. This will return the points of interest. This will return the description vector at each point. Then I will do matching even by using brute force technique or using the nearest neighborhood or whatever the technique you want to use. And you have to specify the norm in this case. In this case, we are using L2 norm. Then you will do nearest neighborhood matching. Then apply threshold to find the best match. Again, if I keep applying threshold and find best match, the correct and the bad, I can plot the ROC curve, if you remember from last time, right? Keep changing this threshold, find the percentage of correct, percentage of false detection, and true positive, false positive, we can plot the ROC curve. Then, based on this good match, I will start to apply the homography between the points of interest I found for those good match here and there. Then I will apply this homography for the coordination of the original box and convert it to the seam box. And it will end up by having, actually it's here, by having this. Is it clear? Any question about this? Okay. So, based on what you can see right now, what are the parameters that I can change here if I didn't find good match between the object and the scene? Starting from the beginning. What exactly I can change here to fine tune this, to find the object if I couldn't find it from the first trial? Because that's exactly what you will do. If you try from the first trial, you will not be able to find the object. You will find always, you will see there is some problem happen. So what exactly you can fine tune in this code? The first step is this minimum Hessian. Reducing this minimum Hessian will give you a chance to have more points of interest. Increasing the minimum Hessian will reduce the number of points of interest. So this parameter will play with the points of interest. The key points that will be generated from here, exactly like the one generated from SERF, which are blobs. So those also are blobs. Second, the matcher itself, the technique we are using for matching, using L2 norm or L1 norm or whatever the technique we will use for matching. Third, the ratio, threshold ratio. What exactly you want to accept, what you want to reject. Finally, the technique used to find the homography. You can use the ransack or you can ignore it. If you are trust that the homography or that the data or the match that you have doesn't have any outliers, then it doesn't make any sense to include the ransack. Why you use the ransack? Use all of them at once and finish your work. You have outliers. In this case, you have to use the ransack technique. So those considered to be the 4 parameters in the code that you can change to adapt or to change the matching problem that you have in your code. Okay? Any problem? Any questions? Again, I will not ask you to build each one of those from scratch because I know that will take time from you to write those type of codes. So we will work with the OpenCV implementation. Now, Assume that I want to use this technique to build a panorama. What does this mean? Assume that I'm having two images for two different views in the scene. And I want to concatenate them together to get an extended view. What's going on here? Yep. So I have two views for a specific scene, and I want to stretch them and extend them to get an extending view for the scene. Okay? How can I do that? Or can I use the techniques we learned so far to achieve this goal? The answer is yes, I can do this. How? Let me stop this. Let's start with this code. So we will start by the basics. What are the basics? First, I will create object detector. Surf, search, surf, whatever the detector that you would like. Okay, here I'm using the surf because surf theoretically is much faster than the SIFT. And when you watch the video, you'll understand exactly why it's faster. Second, I will find the points of interest and the features around the points of interest for all of them. Then I will do matching. Then I will find a good match. Until here, no problem. I'm doing exactly the same thing as we did last time. Then I will start to find the homography between them. When I do the homography, I will, actually let me run it so we can see. When I do the homography, I will transfer one to fit the dimension of the other. So both of them can align together like this. Okay? So after finding the homography, I will go to warp the image. Here, the procedure for the warping. In this case, I'm just do a projected transformation for one image to match the second one. Okay? Then I'm trying to adjust the dimension in a big black background to catch both of them and return the big image. Very straightforward. But unfortunately, this one has a problem. What is this problem? What's the problem? After I converted this to that and attached them to each other to be matching and homogeneous, I think they are matching, right? What?
Somewhat.
So why not?
So values are kind of off.
Which means what?
It's filtering.
The difference in illumination. This one has been captured in a different condition than this. Okay? So can I match them better to do a smooth transition from this to this without this barrier that I have in the middle? Can we? How? The one who said yes. How? Actually, to do this, we need a technique called Laplacian filter. Sorry, Laplacian pyramid. The Laplacian pyramid. So we already know this traditional multi-resolution pyramid, which is the Gaussian pyramid. I have high resolution, Gaussian filter, reduce, Gaussian filter, reduce, and so on. Now, I need here another type of pyramid that I can use to match two different images from two different backgrounds, from two different properties, and the outcome will be smooth transition from one to another. So using this technique, I can generate this version. This one, half apple, half orange. Do you see any transition between them? They are smooth. Okay? How I can do that? This is what we call the Gaussian, sorry, the Laplacian pyramid. How the Laplacian pyramid work? This is the simplest description for it. First, I will start by the original image. Apply Gaussian filter to it. I will get this version, which is a blurred version. I will subtract the original minus the blue. The result will be what? Edges or high frequency components. Then I will reduce the dimension. Then extend it and subtract, get the high frequency again. Then from here, Gaussian, subtract, then extend, subtract, get the other high frequency component. So start with this, apply Gaussian, go lower, then higher, then subtract. So 1, 2, 3. From this, apply Gaussian. Smaller, higher, subtract. Then, actually, Gaussian, smaller, higher, subtract, another high frequency. Gaussian, smaller, higher, subtract, another high frequency. Until I arrive to some level, I will take it as it is. So here I'm having two pyramids. Pyramids of Gaussian and another pyramid of edges, high frequency components. I will call this pyramid Laplacian pyramid. Okay, perfect. I got the Laplacian pyramid. What exactly I will do with that? They said simply, I can reconstruct this image again by combining this smaller one with all those others. I can reconstruct this good frequency or good version. How? So here is the reconstruction of the pyramid first. First, reduce the size. Reduce the size, apply the filter, reduce the size, then increase the size and do the subtract, get with the high frequency components. Then reduce the size again. Up with the size, subtract, get another high frequency component, and so on, until you find or ended up by having this smaller one here, which is this one. This is smaller one. Now, this one, I can scale it up, add it to the edges I got from the previous stage, then scale it up, add it to the edge I got from the previous stage, and so on until I arrive to the same reconstructed version from the original image. Meaning, if I go here, this one, I can scale it up, add it to this, scale it up, add it to this, scale it up, add it to this. This will give me a good approximation or a good estimate for this one. Almost the same, because now I have the high frequency components that always cause problem for me, and the low frequency I will achieve from this. Okay? It's okay, that makes sense. But how can I use this to mix those two images together? This is simply apply or do blend to the image you want to work on. So for example, this is the image of the apple. I want to remove that part. Then hide it. Put black part over it. This is the orange. I want to hide this part. Then I will add black part here. Now, build a Laplacian pyramid for this and Laplacian pyramid for that. So this is the Laplacian pyramid for the apple. This is the Laplacian pyramid for the orange. Now, add those. It will give you this. Add those. It will give you this. Add those. It will give you this. Now reconstruct this from those. It will give you this version, which is a smooth version from this reconstruction. Okay? So using this Laplacian pyramid technique, I can use to merge any two images that's not homogeneous and not match with each other. By building Laplacian pyramid for each part of them, then reconstruct them back. Using this technique, I can, for example, put an eye inside the hand. Or if you recall from lecture number 1, remember this? This is done using the Laplacian pyramid technique. So we are matching the image of Albert Einstein with Marilyn Monroe. Both of them merged together using this technique. Okay? So the same technique can be used here with that. So I can build Laplacian pyramid for this part, Laplacian pyramid for this part, merge them and reconstruct and build them back together. So it will be more homogeneous. Okay? The good news is the OpenCV by default now has a new technique called stitching. This stitching technique or the stitcher this stitcher can be used to combine couple of images together in the same this stitcher can be used to combine several images, all of them have a match with each other using or create a stitcher, and from this stitcher add a list of images you are working with, and based on that it will combine all of them into one big image that match and work homogeneous with each one. This is the result that I show you at the beginning of the panorama. You see? So smooth. Can you see any separator? Nothing. Because they are working on the background with the Laplacian filters. Okay? Sorry, Laplacian filter. Okay? Any question? Any problem? Need to change the time. Okay. So I think we are done for today. One more thing about the project.